Hi, I'm Salvatore Capasso from the University of Salerno in Italy. I'm a student of building engineering and architecture, and I'm going to graduate soon with the thesis research here presented. This is the research team which supported me over the last months within a collaboration between the University of Salerno and the Universidade de Vigo. The topic is a co-rotating rigid beam with elastic hinges for elastic FSI simulations in dual physics with the use of the Project Chrono library. After a brief introduction, we will show how the co-rotating rigid beam numerical model works and how to implement it in the dual physics framework. Finally, we will provide several validations against well-known benchmarks. The aim of this work is to develop an alternative approach for elastic fluid structure interaction with the use of the Project Chrono library, starting from widely used and well-known structural static theories like the Euler-Bernoulli one. We are going to extend them in the dynamic framework. The coupling between the dual physics solver and the Project Chrono library provides a reliable framework for fluid-solid interaction. Using the features already available, like rigid bodies and hinges, so mutual constraints between these rigid bodies, we are going to simulate the flexible behavior of a one-dimensional element by dividing it in rigid trunks and hinges. Here we present the key assumptions of the Euler-Bernoulli formulation. The axis in such a framework is defined by its axis, which is rectilinear in the undeformed condition. We are in the small shifts field. The cross-section is always inalterable and orthogonal to the axis, also in the deformed condition. The material is isotropic elastic. As a consequence of these assumptions, the section is characterized by infinitesimal rigid displacement, which in the two-dimensional Euler-Bernoulli space become the generalized components of displacements. If we evaluate the infinitesimal deformation tensor in a such defined two-dimensional space, we get the generalized components of deformation, which uniquely describes the deformation of the beam. Combining this relation with the internal stress and with the relation which describes the linear elasticity, we get the constitutive bonds for an Euler-Bernoulli beam. Now we present the numerical model. We have seen that the flexural constitutive bond states that the relative rotation between two consecutive straight sections of the beam is proportional to the bending moment. To switch from infinitesimal to discrete quantities, if the length of the trunk, delta zeta, is short enough, we can say that the relative rotation has a finite value too. If we imagine to concentrate this rotation, so the rotation belonging to a trunk in one of its points, which is namely a hinge, placed in one of its straight sections, we get that the constitutive bonds becomes an equilibrium equation in which the only unknown is the local rotation of the hinge. This rotation is again proportional to the moment by a constant, which is the rotational stiffness of the hinge. This is the fundamental element of our discretization, and so our trunk is made up of such defined elements. We have to apply this model to a cantilever because this is the static scheme we are going to deal with in our validation. Once again, this equilibrium equation combined with the rigid body kinematics can provide the displacement function. The boundary condition for a cantilever, theoretically, states that the rotation and the displacement of the first section of the beam are equal to 0, while in our model, we have to allow a rotation for the first trunk to recover a proper numerical result. So the first trunk is considered to be semi-fixed, and so it has a double value of rotational stiffness with respect to the other one. Here we present the dual physics implementation. First of all, we have to insert the element data, the mechanical and geometrical characteristics of the beam. And then the numerical model will provide the discretization of the beam and the dual physics guide parameters, like number and dimension of rigid trunks and the rotational stiffness of every hinge. The result is the chronoscheme. We can see that every trunk is defined as a floating with its own mass, and every rotational hinge is characterized by its rotational stiffness. The first validation is against the analytic displacement function, namely the elastic line equation for a cantilever. To reach the steady state condition in dual physics, we added a linear damper, which does not affect the shape of the deformed beam. The load condition is only gravity, and we have defined the resolution of the problem, dP, as number of particles per straight section. Here we can see the chronoscheme and a video of the simulation. The first chart with the first value of resolution shows that there is rising agreement between our simulation and the analytic solution when the number of trunks increases. But there is a small deviation around the center line of the beam, which is due to the resolution of the problem. In fact, with a double value, our model perfectly reproduces the Euler-Bernoulli solution for a cantilever. The second validation is again a cantilever, but in the dynamic framework. This cantilever plate is subject to an initial velocity distribution, which is defined as starting from those initial conditions. The deflection reference point is the free end of the cantilever, and this simulation is performed in absence of gravity. This is the analytic oscillation function, and we have to say that in this simulation, we are considering only the fundamental mode of vibration, and so this is the fundamental natural system frequency and its relative period. This is the chronoscheme for the dynamic cantilever, and again, we can see that there is rising agreement between the simulation and the analytic solution when the number of trunks increases. On the contrary, with respect to the static validation, this time there is no resolution influence. The first FSI validation is the dam break with elastic gate, following the setup by Antoci et al. In 2007. We have reproduced the elastic gate with our chronoscheme, and the reference point is the displacement of the free end of this elastic gate. This is the chronoscheme of the elastic gate, and so we can start analyzing the visual comparison between the experimental data provided by Antoci et al. And our dual physics simulation. In the first instance of the simulation, we can see that there is a good agreement between our solution and the experimental pictures. And also in the video, we can see that the flexible behavior of the plate is well reproduced by our model. Analyzing the charts, we can see that the first part of the simulation is again well reproduced, while after the peak, our model seems to be excessively rigid. Anyway, it can be compared with competitors SPH and iSPH solvers, like the one proposed by Kayer et al. In 2015. We can see also that there is no sensible variation with the number of trunks. So we are probably dealing with some fluid settings issues. The last validation is against the setup proposed by Liao and et al. In 2015. This is a dam break flow impacting a flexible obstacle. We have 3 markers placed on this obstacle, and the horizontal displacement of these markers is the reference parameter to validate the model. In the visual comparison between the dual physics simulation and the experimental and numerical data provided by Liao, we can see that the first shape of deformation is heavily dependent on the mechanism of releasing of the gate. So the motion of the gates affects the shape of the fluid and of the obstacle at the stage of the first impact. But after this first impact, we can see that our model well reproduces also the shape of the flexible obstacle and of the fluid. Here we can see that our model reproduces perfectly the displacement of the 3 markers, and Also in the video, we can see the flexural behavior. We can note also that our displacement function appears to be more regular. This is due to the fact that the flexible obstacle has only a flexural behavior, so it is not affected by higher modes of vibration. The last consideration about this benchmark can be made about the second impact between the fluid and our obstacle. This simulation in dual physics is executed in single phase, while the reference solution are in multi-phase. So after the impact between the fluid and the right-hand wall, there is no air cavity in the fluid, so no multi-phase flow motion. The fluid dynamic is different and it yields to a higher displacement value of our obstacle. The final remarks about our model: it can be considered robust and reliable just with flexural behavior, can be easily implemented and reproduced because we have only a few simple guide parameters, can be easily be improved with a complete set of mutual constraints by further theoretical investigations. For example, we can switch from the Euler-Bernoulli to the Timoshenko formulation. Thank you for your attention and for this opportunity.